Hi kiddos, it's me again. So now we've moved on to electricity and magnetism, and today I'm going to teach you how to do a problem from 1980, and it's going to be the second electricity problem, alright? Alright, as usual, I'll read it to you. I have my own diagram, and then we'll work from there, okay? Alright. A parallel plate capacitor consists of two conducting plates separated by a distance d, as shown above. The plates may be considered very large so that the effects of the edges may be ignored. The two plates have an equal but opposite surface charge per unit area, sigma. The charge on either plate resides entirely on the inner surface facing the opposite plate. For A, on the diagram below, they want us to draw the electric field lines in the region between the plates. Okay, so basically that is the diagram, okay? Alright, so, moving from there, A wants us, in this diagram, here's the first plate and here's the bottom plate, they want to know the direction of the electric field lines. So, from previous knowledge, we should know that electric field lines move from positive to negative, and they're going to be moving directly down. So, we will draw like this. There's the electric field. Okay, so that wasn't too bad. Now for B, it says, by applying Gauss's law to the rectangular box whose upper surface lies entirely within the top conducting plate, as shown in the following diagram, determine the magnitude of the electric field E in the region between the plates. So, that is the diagram, and that is my attempt. I mean, I started off good, and then the lines messed up there, but it's really not that big of a deal, okay? Alright, so basically we want the field line in the region between the two plates, right? So they want us to use Gauss's law, which is going to be equal to the flux is equal to the closed surface integral of E dot dA, which is the surface area, and that is going to be equal to the enclosed charge over the permittivity constant. So that itself is Gauss's law. Alright, so also we know that sigma is equal to the surface charge per unit area. So that's going to be equal to Q over dA. Alright, so that's sigma. Okay, so from there, we know that the electric field is going to be held constant, so we can take that out of the closed surface integral. So we're going to have E is equal to E times the closed surface integral of dA is equal to the enclosed charge over the permittivity constant. Right there. But, rearranging this, we're going to get Q is equal to sigma times dA. And then, we're going to substitute that in for Q up here. So, I'll show you. So, just using algebra, we get Q is equal to sigma dA. And then we're going to have E is going to be equal to the closed surface integral of dA, which is equal to sigma dA over the permittivity constant. And so we just substituted that in right here. So the dA's on both sides are going to cancel, and what you're going to do basically is just solve for E. So when the dA's cancel, you are left with E is equal to sigma over the permittivity constant. And that is the answer to B. Alright, now one more part. This is an easy one. A dielectric is inserted and fills the region between the plates. Is the electric field greater than, less than, or equal to the electric field when there is no dielectric? Describe the mechanism responsible for this effect. Recognize that the plates are not connected to a battery. Okay, so what do you guys think? Alright, anyway, the electric field is going to be less. And this is because the bound charge distribution in the dielectric is going to have a net negative charge on the top surface, but a positive on the bottom surface of our diagram. And so, thus, when these combined charges are going to be less, and therefore the electric field is going to be less, okay? Alright, I guess that's it for now. We have successfully completed our 1982 Electricity 2 problem. if you have any questions or need any other help, please let me know. Hope you guys have a great night. Bye-bye.